Physics is a truly fascinating subject. It helps us understand the world all around us. From the smallest particles to the largest galaxies, physics explains how things work. Why does a ball fall to the ground? How does light help us see? Why does a magnet attract iron? Physics holds the answers to these questions and many more. It is the science of matter, energy, and their interactions. Learning physics opens up a new way of looking at everyday events and the universe itself. It is a journey of discovery that is both exciting and rewarding for young minds eager to learn. In your Class 10 curriculum, physics plays a very important role. It is not just about memorizing facts and formulas. It is about developing a logical way of thinking. Physics teaches you how to observe, how to question, and how to find solutions to problems. These skills are incredibly valuable. They will help you in other subjects too. They will also help you in your daily life. Understanding basic physics principles can make you more aware of your surroundings and how technology functions. This knowledge empowers you to make informed decisions and appreciate the marvels of science. Moreover, the study of physics in Class 10 builds a strong foundation for future learning. If you are interested in careers in engineering, medicine, technology, or research, physics is essential. Even if you choose a different path, the analytical skills you gain will be very useful. The ICSE physics syllabus is designed to give you a clear understanding of fundamental concepts. It encourages you to think critically and apply what you learn. This preparation is vital for higher studies and for understanding the technological advancements shaping our world. It makes you a more informed citizen. Therefore, as you begin your journey with ICSE Class 10 Physics, approach it with curiosity. See it as an opportunity to explore the laws that govern our universe. Try to connect the concepts you learn with real-life examples. When you understand the why behind a phenomenon, learning becomes much more enjoyable and meaningful. Physics is not just a subject to pass, it is a way to understand the beautiful and orderly nature of the physical world. Embrace this challenge, and you will find physics to be an incredibly engaging and enlightening field of study. Welcome to your study of ICSE Physics for the year 2025. The Council for the Indian School Certificate Examinations, or CISE, has designed a comprehensive syllabus. This syllabus aims to provide you with a solid understanding of core physics principles. It is structured to build your knowledge step by step. You will explore various interesting topics. Each topic will help you see the world from a scientific perspective. The goal is not just to learn definitions. The goal is to understand the concepts deeply. This understanding will allow you to apply them in different situations. Prepare to engage with ideas that explain much of what happens around you daily. The ICSE Class 10 Physics syllabus for 2025 is broadly divided into several key units. The first unit covers force, work, power, and energy. Here you will learn about how forces cause motion and how energy is transferred. Next you will study machines, understanding how simple devices make our work easier. Then, the fascinating world of light awaits you. This includes topics like refraction of light, how lenses work, and the beautiful phenomenon of the spectrum. These concepts explain how we see and how optical instruments function. Each part of the syllabus is interconnected, creating a holistic view of physical laws. Following light, you will delve into the unit on sound. This section explores how sound is produced, how it travels, and its various characteristics like pitch and loudness. After sound, you will encounter electricity and magnetism. This is a very important unit covering concepts like electric current, circuits, resistance, and the relationship between electricity and magnetism, including electromagnets and electric motors. Understanding these topics is crucial as they form the basis of much of modern technology. Household circuits, a practical application of electricity, are also an important part. Finally, the syllabus includes heat and modern physics. In heat, you will learn about calorimetry, specific heat capacity, and changes of state. Modern physics will introduce you to the intriguing topics of radioactivity and nuclear energy, offering a glimpse into the structure of the atom and its immense power. Throughout all these units, the emphasis will be on conceptual clarity, understanding derivations, solving numerical problems, and observing practical applications. This roadmap is designed to equip you with essential knowledge and skills for your future academic pursuits and for life itself. Force is a fundamental concept in physics. It is simply a push or a pull on an object. Forces can cause an object at rest to move. They can also stop a moving object. Forces can change the speed or direction of a moving object. They can even change the shape of an object. We experience forces all the time. When we kick a ball, open a door, or even when we sit on a chair, gravity exerts a force on us. There are different types of forces, such as contact forces like friction, and non-contact forces like gravity or magnetic force. Understanding force is key to understanding motion. Work, in physics, has a very specific meaning. Work is done when a force causes an object to move a certain distance in the direction of the force. If you push a wall and it does not move, you have done no work in the scientific sense, even if you feel tired. The formula for work done is W equals F times S times cos theta, where F is the force, S is the displacement, and theta is the angle between the force and displacement. The standard unit of work is the joule. Work is a scalar quantity. For work to be done, there must be a force applied, the object must move, and there must be a component of the force in the direction of motion. Energy is the capacity to do work. If something has energy, it can exert a force and cause displacement. Energy exists in many different forms. For example, there is kinetic energy, which is the energy of motion. A moving car or a flying bird has kinetic energy. Its formula is Ke equals 1/2 mv squared, where m is mass and v is velocity. There is also potential energy, which is stored energy. An object held at a height has gravitational potential energy, Pe equals mgh. Chemical energy is stored in fuels, and electrical energy powers our devices. The law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. Power is the rate at which work is done, or the rate at which energy is transferred. If you do a certain amount of work quickly, you are using more power than if you do the same work slowly. The formula for power is P equals W over T, where W is work done and T is time taken. The standard unit of power is the watt. 1 watt is equal to 1 joule per second. Another common unit is horsepower. Understanding these concepts, force, work, energy, and power, helps us analyze motion and energy transformations in various systems, from simple machines to complex engines. Key takeaways include their definitions, units, formulas, and the conservation of energy principle. Machines are devices that help us to do work more easily. They can make tasks simpler or faster. A machine can help us in several ways. It can be used as a force multiplier, meaning it allows us to overcome a large resistive force or load by applying a smaller force or effort. It can also be used as a speed multiplier, increasing the speed of work. Sometimes a machine is used to change the direction of the applied effort to a more convenient direction. Common examples of simple machines include levers, pulleys, inclined planes, screws, and wheels and axles. These devices are all around us, often hidden in more complex machinery. To understand how machines work, we use certain technical terms. The load is the resistive force that the machine overcomes. The effort is the force applied to the machine to overcome the load. Mechanical advantage tells us how much the machine multiplies our effort. It is the ratio of load to effort. Massachusetts equals L over E. If MA is greater than 1, the machine is a force multiplier. Velocity ratio is the ratio of the distance moved by the effort to the distance moved by the load in the same time. VR equals dE over dL. It indicates the change in speed. The efficiency of a machine tells us how much of the work input, or work done by effort, is converted into useful work output, or work done on load. In an ideal machine, efficiency would be 100%, but in real machines, some energy is always lost due to friction. Efficiency is calculated as ETA equals work output over work input times 100%, or ETA equals MA over VR. An ideal machine has MA equals VR. Levers are rigid bars that pivot around a fixed point called a fulcrum. There are 3 classes of levers depending on the relative positions of the fulcrum, load, and effort. Class 1 levers can be force or speed multipliers, Class 2 are always force multipliers, and Class 3 are always speed multipliers. Pulleys are wheels with a grooved rim over which a rope passes. A single fixed pulley changes the direction of effort, but has MA equals 1. A single movable pulley has MA equals 2, but does not change effort direction conveniently. Combinations of pulleys, like a block and tackle system, can provide a high mechanical advantage. An inclined plane is a sloping surface that reduces the effort needed to lift an object. In summary, machines are essential tools defined by MA, VR, and efficiency. Understanding levers, pulleys, and inclined planes helps us appreciate their role in reducing human effort and making tasks manageable. Section 5. Light. journey through refraction at plane surfaces. Light is a form of energy that enables us to see the world around us. It travels in straight lines, a property known as rectilinear propagation of light. However, when light travels from one transparent medium to another, for example, from air to water, it changes its direction of travel. This bending of light as it passes from one medium to another is called refraction. The primary cause of refraction is the change in the speed of light as it enters a different medium. Light travels at different speeds in different media. It travels fastest in a vacuum and slower in denser media like glass or water. There are two main laws of refraction. The first law states that the incident ray, the light ray striking the surface, the refracted ray, the light ray that bends and passes into the new medium, and the normal, a line perpendicular to the surface at the point of incidence, all lie in the same plane. The second law, known as Snell's law, describes the relationship between the angle of incidence and the angle of refraction. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. This constant is called the refractive index of the second medium with respect to the first. Refractive index is an important property of a medium. It indicates how much the light will bend. A medium with a higher refractive index is optically denser. When light travels from a rarer medium like air to a denser medium like glass, it bends towards the normal. Conversely, when light travels from a denser medium to a rarer medium, it bends away from the normal. The refractive index can also be expressed as the ratio of the speed of light in the first medium to the speed of light in the second medium. For example, the refractive index of glass with respect to air is the speed of light in air divided by the speed of light in glass. Refraction causes many interesting natural phenomena. For instance, a swimming pool appears shallower than it actually is due to refraction. This is because the light rays coming from the bottom of the pool bend away from the normal as they exit the water into the air. Our brain perceives the object based on the straight path from which the light appears to come. Similarly, a pencil or stick partly immersed in water appears bent at the surface. Understanding these principles of refraction, Snell's law and refractive index is crucial for studying how lenses work and for explaining various optical illusions and atmospheric effects. Section 6. Light, lenses, and the colorful spectrum. Lenses are transparent pieces of glass or plastic, usually with curved surfaces, that refract light to form images. There are two main types of lenses: convex lenses and concave lenses. A convex lens is thicker at the center and thinner at the edges. It converges parallel rays of light to a point, so it is also called a converging lens. A concave lens is thinner at the center and thicker at the edges. It diverges parallel rays of light, making them appear to come from a point, so it is called a diverging lens. Lenses are used in eyeglasses, cameras, microscopes, telescopes, and many other optical instruments. The behavior of light passing through a lens can be understood using ray diagrams. Key terms associated with lenses include the optical center, a point within the lens through which rays pass undeviated, principal axis, a line passing through the optical center and perpendicular to the lens surfaces, and principal foci, points where parallel rays converge or appear to diverge from. The image formed by a lens can be real or virtual, erect or inverted, and magnified or diminished, depending on the type of lens and the position of the object. For example, a convex lens can form a real inverted image if the object is beyond its focal point, or a virtual erect magnified image if the object is within its focal point, like in a magnifying glass. The relationship between the object distance, u image distance, v, and focal length, f, of a lens is given by the lens formula, 1 over f equals 1 over v minus 1 over u. Magnification, em, produced by a lens is the ratio of the height of the image, h prime, to the height of the object, h, and is also given by m equals v over u. The power of a lens, p, is a measure of its ability to converge or diverge light. It is the reciprocal of its focal length in meters, p equals 1 over f. The unit of power is the diopter, d. A convex lens has positive power and a concave lens has negative power. Another fascinating phenomenon related to light is dispersion. When white light, such as sunlight, passes through a prism, it splits into its constituent colors: violet, indigo, blue, green, yellow, orange, and red vibrure. This band of colors is called a spectrum. Dispersion occurs because the refractive index of the material of the prism is slightly different for different colors of light. Violet light bends the most, and red light bends the least. Rainbows are a natural example of a spectrum formed by the dispersion of sunlight by raindrops. Understanding lenses, their image formation properties, the lens formula, power, and the phenomenon of dispersion is fundamental to optics. Section 7 Sound, the world of vibrations and waves. Sound is a form of energy that we can hear. It is produced by vibrating objects. When an object vibrates, it causes the surrounding air molecules to vibrate as well. These vibrations travel outwards from the source as waves. Sound waves are longitudinal waves, meaning the particles of the medium vibrate parallel to the direction of wave propagation. Think of a slinky spring. If you push one end, a compression travels along the spring. Sound travels similarly, creating regions of compression, where air particles are close together, and rarefaction, where air particles are spread out. Sound needs a medium to travel. It cannot travel through a vacuum like outer space. There are three main characteristics that distinguish different sounds: loudness, pitch, and quality, or timbre. Loudness is related to the intensity of the sound wave, which depends on its amplitude. A sound wave with a larger amplitude is louder. Loudness is measured in decibels, dB. Pitch refers to how high or low a sound is. It depends on the frequency of the sound wave. A higher frequency means a higher pitch, like the sound of a whistle. A lower frequency means a lower pitch, like the sound of a drum. Quality or timbre is what helps us distinguish between two sounds of the same loudness and pitch, but produced by different instruments or voices. It depends on the waveform of the sound. Sound waves can be reflected, just like light waves. The reflection of sound from a hard surface is called an echo. To hear a distinct echo, there must be a minimum time interval of about 1/10 of a second between the original sound and the reflected sound. This means the reflecting surface must be at a certain minimum distance from the source, around 17 meters in air. Prolonged reflection of sound in an enclosed space is called reverberation. This can sometimes be undesirable in concert halls, leading to a blurring of sound. Sonar, sound navigation and ranging, is a technique that uses sound reflection to measure distances underwater or detect objects. Objects can vibrate in different ways. Natural vibrations occur when an object is disturbed and then allowed to vibrate freely at its own natural frequency. Damped vibrations are when the amplitude of vibrations gradually decreases due to resistive forces like air friction. Forced vibrations occur when an object is made to vibrate by an external periodic force. If the frequency of this external force matches the natural frequency of the object, a phenomenon called resonance occurs. During resonance, the object vibrates with a very large amplitude. Examples include a swing being pushed at its natural frequency, or a wine glass shattering from a specific sound frequency. Understanding sound production, propagation, its characteristics, reflection, and vibrational phenomena is key. Section 8, Electricity and Magnetism, the Flow and Pull. Current electricity deals with the flow of electric charges. An electric current is the rate of flow of charge, I equals Q over T, measured in amperes, A. For a current to flow in a conductor, there must be a potential difference, voltage, across its ends. Potential difference V is the work done per unit charge to move a charge between 2 points. V equals W over Q, measured in volts. V, resistance R, is the opposition offered by a conductor to the flow of current, measured in ohms omega. Ohm's law states that the current flowing through a conductor is directly proportional to the potential difference across its ends, provided the temperature remains constant, V equals IR. This is a fundamental law in electricity. Conductors have low resistance, while insulators have very high resistance. The resistance of a conductor depends on its length, cross-sectional area, material, resistivity, and temperature. Resistors can be combined in circuits in two main ways: series and parallel. In a series combination, the same current flows through all resistors, and the total resistance is the sum of individual resistances. In a parallel combination, the voltage across all resistors is the same, and the reciprocal of the total resistance is the sum of the reciprocals of individual resistances. Electrical energy is the energy consumed when current flows, and electrical power, P equals 6 equals I squared R equals V squared over R, is the rate at which electrical energy is consumed, measured in watts, W. Electromagnetism is the study of the relationship between electricity and magnetism. A current-carrying conductor produces a magnetic field around it. The The pattern of this magnetic field can be visualized using magnetic field lines. For a straight conductor, the field lines are concentric circles. For a circular coil, the field is stronger at the center. A solenoid, which is a long coil of wire, behaves like a bar magnet when current flows through it, with a north and a south pole. The strength of an electromagnet depends on the number of turns, the current, and the presence of a soft iron core. Electromagnets have many applications, like in electric bells and cranes. When a current-carrying conductor is placed in an external magnetic field, it experiences a force, motor effect. The direction of this force can be found using Fleming's left-hand rule. This principle is used in electric motors, which convert electrical energy into mechanical energy. Conversely, when a conductor moves in a magnetic field, or when the magnetic field around a conductor changes, an electromotive force and hence current is induced in the conductor. This is called electromagnetic induction, discovered by Faraday. This principle is used in electric generators, which convert mechanical energy into electrical energy. Understanding Ohm's law, circuits, magnetic effects of current, and electromagnetic induction is vital. Section 9. Heat, Modern Physics, and Mastering Your Exams. Heat is a form of energy that flows from a hotter body to a colder body. Temperature is a measure of the degree of hotness or coldness of a body. When a substance absorbs heat, its temperature usually rises. The amount of heat energy, Q, required to change the temperature of a substance is given by Q equals mc delta T, where m is the mass, C is the specific heat capacity, and delta T is the change in temperature. Specific heat capacity is the amount of heat required to raise the temperature of unit mass of a substance by 1 degree Celsius, or 1 Kelvin. Water has a high specific heat capacity, which is why it is used in car radiators and as a heat reservoir. Calorimetry is the measurement of heat. The principle of calorimetry states that when a hot body and a cold body are in thermal contact, the heat lost by the hot body is equal to the heat gained by the cold body, provided no heat is lost to the surroundings. This principle is used to determine the specific heat capacity of substances. Heat is also absorbed or released during a change of state, like melting, freezing, boiling, condensation, without any change in temperature. This heat is called latent heat. Latent heat of fusion is for melting or freezing, and latent heat of vaporization is for boiling or condensation. For example, ice at 0 degrees Celsius absorbs latent heat to become water at 0 degrees Celsius. Modern physics introduces you to radioactivity. Radioactivity is a spontaneous phenomenon where unstable atomic nuclei disintegrate, emitting radiations like alpha particles, beta particles, and gamma rays. Alpha particles are helium nuclei, beta particles are fast electrons, and gamma rays are high-energy electromagnetic radiation. These radiations have different properties in terms of their penetrating power, ionizing power, and deflection in electric and magnetic fields. Nuclear energy is released during nuclear reactions like nuclear fission, splitting of a heavy nucleus, and nuclear fusion, combining of light nuclei. These processes release enormous amounts of energy. To master ICSE physics, consistent effort and a clear understanding of concepts are key. Start by reading each topic thoroughly. Focus on understanding the definitions, laws, and principles rather than just memorizing them. Practice drawing neat, labeled diagrams for optical phenomena, circuits, and magnetic fields. Solve a variety of numerical problems, starting with simple examples and gradually moving to more complex ones. Make a list of all important formulas and units for quick revision. Regularly review what you have studied, and try to explain concepts in your own words. Solving past year's question papers will help you understand the exam pattern and manage your time effectively during the examination. Physics can be very rewarding with the right approach.